Hi, my name is Leonardo and I'm here to show you a bit more about EMC and the effects of discontinuities on PCB boards. I am a PhD candidate here at the University of Twente and I am enrolled with a project called Easier. So let's get to it. Okay, here we have the discontinuities board with some signal input ports on the left side and output ports on the right side, and they are interconnected by traces. They are actually connected to the VNA, which measures the ST1 parameter, which is the ratio of the received signal and the input signal by those two cables. So the VNA was calibrated for a frequency range between 1 MHz and 1.3 GHz. And for a load of 50 ohms, which I can show you right here in my screen. Let's just do a sweep. Well, you can see that it's nice and smooth. So let's just go to the experiment. Let's start with the first trace. So the first trace, you can see that's thicker than the second one. This is actually because of the properties of this trace will result in different parameters. In this case, impedance. This impedance is rated at 50 ohms, which should match which was calibrated to the VNA. So let's take a look. Now I'm going to run another sweep and we can see how it behaves. Well, you can see that they are basically behaving the same way, besides some effects on the higher frequencies, and it's mainly resulting to the manufacturing process of this board. Okay. However, if we change to the second trace actually is much thinner, so we can see that the properties are going to change. The second trace actually has an impedance of 120 ohms, so we're going to see how it reflects on the sweeping. So now with the input and output ports for the second trace, we're going to make a sweep and see how it behaves. Well, you can see that the second trace has a higher impedance, which is 120 ohms, and it has a reflection on lower frequencies. So it's mainly because you have a 50 ohm signal coming and just changing to a 120 ohm impedance line and then changing again to 50 ohm load. So you can see those reflections in the blue trace. So here we have the third line. So the third trace is actually a mixture of a hybrid of the first two. So we have the first half with the same impedance as the first trace, and the second half with the impedance of the second trace. So you have 50 and 120. So let's run a sweep and see how it behaves. You can see with the pink trace that the attenuation happened at lower frequencies, but differently from the whole 120. So let's talk about the fourth track. It's a bit different than the others, and you can see two junctions, one here and one other here. So what happens is that the signal comes this way, it splits in two different arms, and when it comes this way, it bounces back, adding to the upcoming wave destructively, doing the same thing here, and the result we can see here in the trace. Okay, now we have a different situation here. You can see that now we actually loaded the other two connectors with a 50 ohm load, so they're basically the same. Even though we loaded it, we will have a different result here in the trace. However, you can see that the power input in here actually got dissipated between the three paths. So what goes to the VNA is actually lower than it was if, let's say, we would have the second trace. So in the purple trace we can see the combined effect of those jump impedances and this mismatch impedance from 120 to the 50 ohm load, those 120 to the 50 ohm loads, and the partial reflection because part was absorbed by loads. Besides that, we can actually see that the power was dissipated between the three loads, and just part of the power was actually received by the output port. We've seen that the design part of the trace is very important because any discontinuities that we implement in the trace, it can be jump impedances, well, any sort of discontinuities can actually compromise the board and the behavior of the system. So with the ground slot or ground aperture board, we are intending to see how the current flows when the returning path is interrupted, let's say with a ground aperture in a PC board. So here we have the PCB board, the ground slot board, which has 3 tracks with 3 input ports and 3 output ports. So to operate this board, actually we are going to input a signal coming from the signal generator through this cable, to which we connect to one of the input ports, and then we load the output port. So here we have the sniffer. Actually, the sniffer is a ferrite core with a coil winded right here, and it captures actually the magnetic field coming from a current on a specific path right in the middle. Well, the signal generator is actually triggering the oscilloscope, and with the aid of a second channel and the sniffer, we are going to observe how the current behaves in this board. So we can see that the current is flowing along the track 2, which is, by the way, a reference track without any discontinuities in that, and it goes up to the end. Well, let's talk about the third track. In the third track, we introduce an aperture or a ground slot, and you can see that actually this track has a signal that comes straight from the input to the output. However, the return path is interrupted by this slot. What happens is that this slot represents a capacitance, and the higher frequencies, they see this capacitance as a lower impedance, therefore they would choose this as a returning path. But for lower impedances, we need to choose the second best option, which is, you can imagine, coming from a straight line from the output to here in the extremity of the ground slot. However, I'll show you in a bit, this path in the proximity of the ground slot and the track will represent the smallest loop possible. Therefore, the lower frequencies will choose to come alongside the track and the ground slot, and the higher frequencies just through the capacitance. Well, let's see how it behaves when we set up this track. With the sniffer, you can see that the signal represented by the positive peak is actually going alongside the track. However, the return path represented by the negative peak is actually present right into the edge of the ground slot. So you can see that we have here the peak of the returning path or the returning signal, and it goes around. However, if I deviate or if I just go further from the ground slot, the signal starts to get lost. So it proves that the current actually comes alongside the track, and when it goes alongside the ground slot, you can see the return path. So now let's talk about the first track. As you can see, it has also a ground slot, but it's much bigger than the third one. So let's first set it up, the load and the signal, and with the help of a sniffer, let's see how it behaves. You can see that the current is flowing until the load, And similarly to the third one, you can see that the return path is right up to the edges of the slot. So now you can actually see that we have two switches here. What the first switch does, it actually creates a return path parallel to the signal. So when I press this, you can see that the signal is going to choose coming back through this newly created path instead through the slots. This is due to this path having a much smaller impedance than the loop created. You see, the signal is reduced. Now you have the second switch. The second switch also has connected a capacitor. Let's see what happens. Well, you see that the signal is reduced. The message that you can get here is that even though we have a capacitor, the impedance introduced by this capacitor is smaller than the impedance introduced by the loop created by the slot. I hope this video helped you to get a better understanding on how current flows and how it chooses its path through the lowest impedance mediums, and the effects towards EMC. And what happens to the signal itself, you already know from the video of self-inductance.